Assalamualaikum, students and friends. Welcome back to Sir K Loves Physics tutorial. Today's episode is a revised excerpt of a past upload on relativistic energy. It puts emphasis on the difference between rest energy and relativistic energy. So join me till the end of this video. Just relax, watch, and learn. The total energy of an object can be expressed, all right, in terms of this equation, where capital E stands for the relativistic energy of a body. It is equal to the rest energy, m naught times c squared, where c is the speed of light. That is divided by square root of 1 minus b squared over c squared. All right, so the quantity in the denominator is also known as the reciprocal of Lorentz factor, sometimes denoted by the letter gamma. All right, so the rest energy of an object is expressed as capital E naught equals m naught c squared. This is based on Einstein's famous equation E equals mc squared. But here we're emphasizing that the energy, or E naught, pertains only, all right, to the rest energy of a body or an object. Now, when a body is in motion, all right, with a speed that is comparable to the speed of light, then we can also describe its kinetic energy relativistically, and that is just determined by getting the relativistic energy, capital E, minus the rest energy E naught. That is, the kinetic energy, all right, of any particle with a substantial speed comparable to the speed of light. All right, Ke here is the relativistic kinetic energy, and that is equal to m naught c squared divided by the square root of 1 minus b squared over c squared, all right, minus m naught c squared, all right, which, when expressed in terms of Lorentz factor gamma, all right, we have this equation, Ke, or relativistic kinetic energy, is equal to gamma minus 1 multiplied by m naught c squared, while the total relativistic energy, capital E, is equal to gamma multiplied by m naught c squared. For question number 2, the sun radiates electromagnetic energy at a rate of 3.92 times 10 to the 26 power watts. Question letter A, what is the change in the sun's mass during each second that it is radiating energy? Letter B, what fraction of the sun's mass, estimated to be equal to 1.99 raised to the 30th power kilogram, is lost during a human lifetime of 75 years? So for our solution, we first compute the change in the mass, delta m naught, which is based on the formula for rest energy, delta E naught. When you divide that by the square of the speed of light, then we will get the change in the mass m naught. All right? Substituting, we have 3.92 times 10 to the 26th power watts or joules per second. Multiplying that by 1 second or 1.00 second and dividing the whole thing by the square of the speed of light, then we will get the value for the delta m naught equal to 4.36 raised to the 9th power kilogram. Take note, this is the mass of the sun that is lost in every second. But strictly speaking, it is not actually lost, but it is just transformed into energy. Now for question letter B, what fraction of the sun's total mass is this delta M equivalent to? Alright, so we determine the ratio delta M naught over the sun's mass. Substituting, we get 4.36 times 10 to the 9th kilogram per second. Alright, and multiplying it by the length of time, 75 years is already converted here into seconds. That is 2.37 times 10 to the 9th power seconds. Dividing the whole thing by the estimated mass of the sun, 1.99 times 10 to the 30th power kilogram, then we will get the ratio of delta M naught over delta M, or the mass of the sun, equal to 5.19 times 10 to the negative 12. Alright? So this number simply shows how small this change in the mass in every second, alright, when compared to the total estimated mass of the sun. Our last question, number 3. At what speed is a particle traveling if its kinetic energy is 3 times its rest energy? So our solution, we express the relativistic kinetic energy, okay, equal to m naught c squared over square root of 1 minus b squared over c squared minus the rest energy m naught c squared. And that is equated to 3 times the rest energy, okay, based on the given question. Alright, so we can transpose m naught c squared, alright, to the right side of the equation, so that we will have 4m naught c squared, and our equation now, alright, becomes m naught c squared over 4m naught c squared, alright, when we transpose 4m naught c squared to the left side of the equation, while square root of 1 minus b squared over c squared is also transposed to the right side of the equation. So it's clear that we can cancel out m naught c squared, and that will leave us only with 1/4, or in decimal, that's 0.25. And if we're going to square both sides of the equation, alright, that will enable us to eliminate the radical sign. And isolating v squared, or negative v squared over c squared, we will have v squared over c squared equal to 1 minus 0.0625, which is the square of 0.25, right? That means to simplify b squared over c squared, then we have to get the square root also for the quantity on the right side, alright? So v over c becomes square root of 1 minus 0.0625. And we simplify further, alright, by getting the square root of 1 minus 0.0625, which is 0.968, and multiplying that by the speed of light c, we finally get the value of the speed that we want, all right, equal to 2.90 times 10 to the 8 meters per second. So this computed speed is comparable to the speed of light, all right. It is such a substantial speed that will make the kinetic energy or relativistic kinetic energy of the particle 3 times as large as its rest energy. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.